All right, everybody, welcome to another lab session. Today we are going to be, I see that my title is wrong now. Today we are not going to be talking about data visualization. We're going to be talking about statistics and machine learning, or the basics of machine learning. We will not get it too in-depth today, but we're going to start to dabble into them. So for today's class or lab, what we're going to be looking at is some weather data. And you'll notice here in our documentation, lines 15 through 29 are a bunch of different resources. Because we're moving into more complex topics, I assume it makes it more complex for you to learn. So I will do my best over the next 3 to 4 weeks to be able to provide you with as many references and resources as possible. To start, what we need to discuss are some simple concepts. So assuming that you watched my lecture from Monday, we talked about linear regressions and linear models, as well as multiple regressions. And a linear regression is a linear approach for modeling the relationship between a scalar response and one of its explanatory variables. So the scalar response is what I was referring to as the response variable, which is also commonly called the dependent variable in statistics. And then the explanatory variable explains the change in response, and that is what we'd commonly refer to as our independent variable in our model. So basically, to put it simply, the linear model is a way of plotting X versus Y and coming up with a formula and a model that has assumptions that allow you to plot your data and look at the relationship between your points. And the important part about linear modeling is, one, it's incredibly commonly used. Like every single scientific experiment essentially uses some form of a regression. And we have to, because we need to be able to plot out these points. But the important part of linear regression in general is, one, it tells us the correlation or the exact, I shouldn't say exact, the finite relationship or association between multiple variables. And it also gives us a way to try to predict the change in the response variable based on that relationship or association to their explanatory variables. So we are going to start talking about this linear modeling today. And we are also going to get a little bit into linear mixed modeling. And linear mixed modeling, if you haven't covered it yet in the math class, I don't expect you to dive too deep in it. The important part for right now is, think of linear modeling as y equals mx plus b, which is shown right there. And you've probably talked about a bunch of times before in your statistics class or math class. And linear mixed modeling or mixed effects modeling is almost the exact same thing, except we add in a random effect. And this random effect can be anything that you feel may be having a random effect on the way that your data is being modeled. So like, for instance, today we're going to be working with weather data. So an example of a random effect that could be affecting the precision or the accuracy of our weather data could be which weather station it was recorded at. So if we were doing traditional multiple or multivariate regression or statistical analysis, we possibly would include this the weather station that we collected the data from as our random effect. So that's the basics of the statistics that we need to cover for the day. As far as packages that you'll need for today, just a reminder that, one, our files are uploaded on our Discord server already. And then two, for the packages you'll need to install to be able to work along with me today, you'll need this package called Stats Model. And the reference to that is in our on line 17. And then we have also scikit-learn. Scikit-learn is going to be the basis for probably the next 3 weeks worth of work that we do. And scikit-learn is on line 19. So I think with that, we're kind of caught up for where we are going to be heading today. Yes, the other concepts we'll talk about once we actually get to them and we need to use them. And then I also point out to you that, as always, I provided you the references for the stuff that we're going to be working on today. So like our practice code, For the multiple regressions we'll be doing when we first get into machine learning at the very bottom of this class is this first tab right here. It's Kaggle. Kaggle is or Kaggle, however you want to say it, is a data science repository. So they have a bunch of free data that you can come and grab. This one I thought was very simple in its explanation of machine learning and how to iterate over a model. And that's why we'll be using it today. Anything else? And then this other link right here that says ARIMA algorithm. That is a specific algorithm that is commonly used to predict and forecast weather. So there's another link there, essentially doing the same thing that we're going to do today in class from the code on line 26. But with the ARIMA algorithm, you have a slightly different way that you implement the algorithm in Scikit. So before we get started, as you guys know, I am big on our data checklist. I want to make sure we understand what we're talking about. So today, we are going to be working with data from here in the Valley, from Yakima, Washington. This data comes from a weather station located on Atanum Drive, or Atanum Boulevard, I don't remember, but on Atanum. And so essentially, it's been recording data since 2008. So I went all the way back and collected the data from 2008 up until today, 2023. So we have, let's see, 15 years worth of data, and I think 6,000, almost 6,000 data points. And we'll see we've got our standard formatting for the date with slashes or dashes for every year. We have a secondary date column that shows us just the single numeric value for that date. We've got the minimum temperature in Fahrenheit, the average temperature in Fahrenheit, the max temperature in Fahrenheit. This is the average 1.5 meter DP is dew point. So how much precipitation is in the air, or the temperature to condense into a water droplet is dew point. G is our relative humidity. LWU, I can tell you right now, we don't need that. I'm not even going to worry about it. Average direction is the wind direction, the prevailing wind direction for the day. Notice that this is a categorical variable, right? It's either going to be north or south or west or east or southwest or southeast, whatever it might be. So if we wanted to include this in our analysis, we would have to refactor this or come up with some kind of coding and key value pair system to change these to a number. Speed, miles per hour, is the wind speed. The max gust speed is a 2-minute long measurement of the maximum speed at that point in time. 2-inch degrees Fahrenheit, I don't think we have any data points for that, so it probably can just be deleted. Minimum F1, don't worry about that. Average F1, don't worry about that. Total precipitation for the day, total solar radiation for the day. ET is the evapotranspiration. If you guys don't know, we live in a desert technically. So when the sun is beating down on us in the summer, all that's happening is water is evaporating out of the ground. So weather stations are capable of measuring that. So it's got the ETO and the ETN. There's a difference there. Let's see. Let's go back to our browser here and go look up evapotranspiration definition, or actually let's go with formula, because they give us both of the measurements to calculate the average evapotranspiration. So here they are. ETO ETO crop evapotranspiration is calculated by multiplying ETO by Kc, a coefficient expressing the difference in evapotranspiration between the cropped and reference grass surface. So that is what they're providing us here. The ETO is the base, the ETR is the relative for that area. So clearly in this instance, for the actual formula, ETC is the evapotranspiration of the crop that we're measuring. For this weather station, it does not have a crop evapotranspiration to compare to. So they're using an R. Without looking at the exact metadata for the data set, I'm not sure what the R is for, but we could still implement the formula if we wanted to. So that is the basics of our data set. Of course, we'll go through our data checklist as we get through this process. But as of now, does anyone have any questions for me? Silence, which I assume means
I have
that
a question.
yeah,
Does
what's
the
up?
does the data sheet have like wind speeds and stuff like that? And any other information, or just all you just covered?
What do you mean the data sheet? Yes,
Oh,
is
because I
this
don't know.
right
I
here
was
the
I was kind
average
of
wind
curious.
speed?
Oh, sorry.
No, you're good. This right here is the average wind speed in J, and then in K is the maximum gust of the wind in a 2-minute interval.
Yeah. Okay.
Okay.
It's because I was kind of curious on this because I did an internship on this
Oh, okay, cool. Where with or who with?
with Washington State University.
Okay, so you were working on the Ag WeatherNet?
Yes.
Okay, nice. Yeah. So the Ag WeatherNet, for all those that are not familiar with it, the Ag WeatherNet is a network of stations, and I've used that data. We actually could have used it today. Let's look at I think it's just agweathernet.com. Oh, weather.wsu.edu. And you can pull up weather stations across the entire state. I don't know how many they're up to now, but it's quite a few. So
300.
300.
Yeah.
Yeah, that's pretty good. So they have all of these around Washington, and of course, you know that they're going to focus on the cropping regions. That's why they started to build this, is for mathematical modeling of pest incidence levels and bud break time for the trees and those kind of things. But you also can come collect this data year by year for yourself for a bunch of different metrics. And then there's another company called Simios, and they are a pesticide company, but they have customers all the way up from Kelowna, British Columbia, down through Los Angeles. So basically, the entire West Coast, you can get open source weather data from them too. But that's pretty cool. So you've already worked with this data then, Robert, or similar data, right?
Yeah, but I haven't used the ML with machine learning part on
Oh,
this. I did it within HTML and
okay.
JavaScript.
So you were doing web applications.
Yeah.
Nice. Okay, cool. Yeah, so we'll expand on that today, basically. So we will just go ahead and get started then. So I'm going to start by navigating over to my virtual environment. And why are you telling me? Oh, I spelled desktop wrong. That's why. And I'm going to do it again. All right. List what's in there. There's my environment shown in blue. Dat.sci. Weather is an object that I accidentally saved to this folder. It is, or no, weather is another folder in there now, actually. Excuse me. I or exported everything as a folder on accident. Anyways, let's go ahead and activate our virtual environment. So source dat.sci /bin/activate. Okay, we're good to go. I'm going to log into Python 3 there, and now we are active. So if you did not already download the packages for today, you just need to use pip install or pip3 install, and then scikit-learn and stats models. Activate your virtual environment. After you get that done, then we are going to have a bunch of imports today as far as our packages go. So we are going to import NumPy, we're going to import pandas, we're going to import matplotlib, we're going to import Seaborn, and then we're going to start by just importing the linear regression algorithm from scikit-learn. We're not going to download, or we're not going to import all the stuff we need right away for that. So I will shift enter and run those, just save us a couple seconds. Then we are going to import our data set. So I'm going to call it weather, just a nice, plain, easy to remember objects. And we are going to call that as PD for pandas, read_CSV, and then the location of your file. All right, enter, good to go on that. Let's print out weather and see if we have anything good going on there. Oops, can't spell again. All right, there we go. So we've got our data showing up here. Like I said, I thought we had about 6,000 rows. It looks like we have about 5,000 rows, but that's still a lot of day by day data to work with. It looks like everything was read in correctly so far, right? I don't see any errors. I do have one bone to pick with the data set, and that is how everything is formatted as far as column names go. Like having this temperature symbol in your column name is horrible. I bet almost none of you, does anyone, actually, let's ask it as a question. Does anyone know how to type out the degree symbol on a keyboard?
Degree symbol.
Mm-hmm. It's okay. It's just like
Is it
a,
Windows Shift? And I think like period, because I think that brings up. I don't remember.
I know for sure Alt 248 or Windows Shift 248 probably does it too, but that's not like a really easy thing to type. So my point is like we need to, if we want to keep this column or even the total solar radiation, we don't need the unit measurements in the title. So that's one really quick obvious change we can make to save ourselves some time. Why don't we rename these columns? And then, of course, we'll do all of our normal checks too. But that's one thing I'd like to change right off the bat here. So let's go ahead and start working through our data checklist. So step one is get familiar with the data set. So my question to everyone, as always, is do we understand all the variables and what the data set, what information the data set is providing us? Since we've already covered it, I'm going to assume yes. And I also think that we are in a position where we should understand weather data. It's fairly simple overall. The one thing that may be weird is the evapotranspiration or the total solar radiation, which is total solar radiation is just the amount of sunlight that is making it through the atmosphere and touching that weather station or being recorded by that weather station. Let's look at our weather.info. I don't think I've shown you guys this before, but this is a different way of examining basically your data types all in one place. So this kind of speeds up and narrows down the need for the data checklist, but not every programming language uses this. That's why I still have the data checklist in place. But this shows us all of our column data, the non-null data, as well as the count for non-null data points, and then the data type. So we kind of got three things in one here, which really saves us quite a bit of time. Two less key pushes on our keyboard, basically. And we can see right now, we can see that everything has the exact same number of data points except for column number 11, which is the 2-inch degrees Fahrenheit. And which I told you guys, I'm not even necessarily sure what that is in a measurement of, but we're missing 5,354 data points. So clearly it's not providing us with any kind of useful information, at least from this weather station. Another thing that I see as we move into number 2 and number 3 here, another thing that I see is that we're measuring or we're representing a lot of these columns as objects. Like for instance, the date is an object. That's okay. Date time can read it as an object, I believe. But like our temperatures are read as objects. Our relative humidity is in a float. Our dew point isn't an object. Our wind direction's an object. Our wind speed is an object. So that doesn't necessarily make sense. So that I would consider to be an irregular format. And I would say that we probably need to adjust that. So we've got a couple of changes we can make here right away. The first thing we should do is start with, I guess, our structural errors. So the first thing I would like to do is rename. Probably 6 one way, half dozen the other. Let's not do that. First thing I want to do is select the columns that we want to keep for the data set. But in order to do that, we have to we have to come up with our questions that we'd like to answer with this data set. So number one for me, for our questions are going to be, let's say, is temperature accurately predicted by one independent variable? And if that doesn't make sense to you, it will make sense here in a minute, because we're going to do some exploratory data analysis and try to find which of these variables may be most correlated to our temperature specifically. Two, let's say, how many variables are needed to accurately fit a ML model? Does anyone else have a question? Or Robert? I'm just going to call you out now, Robert, because I know you'll talk. So Robert, do you have any questions? Or Juan or Evelyn or Bethany, whoever.
Can we do a correlation?
Oh yeah, absolutely. We'll do a correlation here in about 2 minutes. Which one you got?
I guess we could do it has times, right? So we could do like a correlation between dates and however like wind gust speeds, or I don't know, or like averages.
Okay.
Time.
So, oh yeah. So wind is instead. I was my brain was stuck on temperature. You want to focus on wind. What's the correlation between wind?
Well, we could work with temperatures. I said a lot of things at once. I'm sorry.
No, you're good. It doesn't matter. So we'll say, what's the correlation between wind and date? And that actually will be kind of interesting, because we can look at, do we have higher wind gusts or gust of wind at certain times of the year? Which, based off of living here, I would assume the assumption is yes, or that the answer is yes, because, for instance, in the winter we have air inversions, which causes all the air to settle. So I assume once an inversion blows in, we do have some kind of large shift in our average gust speed. So that'll actually be kind of interesting. So yeah, let's stick with those three and see if we can answer them for the day. And that really narrows down the variables that we have to keep here. So we clearly we always need to keep our date. I'm just going to write myself a note under here too. And I'm going to say columns to keep. What is squeaking? That's annoying. Columns to keep. I definitely want to keep date. Do we care about minimum versus maximum temperature? Or are we cool with just average?
I don't think it's necessary.
Okay.
If we have an average.
Yeah, exactly. I agree with you. So we're going to do average F. I'm going to do average dew point, average relative humidity, just because those are more specific environmental characteristics that'll help with the machine learning model. Average speed, which is our wind, average or max gust, max gust. We don't need those. Total precipitation, I'm interested in that. And then total solar radiation. Evapotranspiration, we have all the data for it, actually. Yeah, but we'll have to calculate the evapotranspiration. No, we don't have to. We'll keep ETO since it's our baseline, because that still provides us some useful information. But we'll get rid of the ETR just for now. And again, this is not perfect. We're just simplifying things down so that we can, make some progress. All right, so now we're at a point where we can select the columns that we actually want to keep. So we're just going to have to type them in there as they are shown in the data set for now, which I know is annoying, but we'll rename them next. So we're up here on line 76 where it says weather equals weather, and then double brackets, and you're just going to list your columns inside of there with single quotations, average F. See, and this is why I don't like having these awkward names, is because now instead of being able to type them in, I have to go over there and copy and paste them. So it's just annoying. But you know, that's a personal issue, I suppose, and we will change them as soon as we can. All right. While you are waiting on me to do this, does anyone have any questions about the homework that is now due on Friday, I believe? Perfect. I love simple. Speed. Oh gosh. And then 2M. Total precipitation. Don't worry, it'll speed up here in a minute. We just have to get through these, and then after that, we'll be ready to do some basic analysis stuff. And we also have to do our conversion, our type conversions, but and then ETO is our last one. All right, let's run that line. Boom, read in just fine. Let's now, let's print weather real quick, make sure it did run. And we're down to 9 columns instead of 18. So we cut it directly in half, which is good. Let's go ahead and do our rename function. And I'm just going to grab this entire string here, copy it down here into our rename function. And then we're going to, of course, have to change things up. Let me go and double check that we remember how to do this. Pandas, rename, geeks for geeks. Columns rename, and let's look for a different example. And this is the mapping that we're going to need. So it's rankings underscore PD, which is the name of the data set that you can see right here. And then we're going to do rename function columns equals, and then the mappings of them. So we need to change our syntax from the brackets. And we're going to write the word columns equals, and then we're going to create our key value pairs. And each one does not have their own, they just have their own names. So we'll actually keep date the same. I'll just lowercase it instead. Average is going to go to avg underscore f. Average dew point is going to be mapped to avg underscore dp. Average relative humidity will be mapped to average RH. How did I do that? There we go. avg underscore RH. Speed. This one, wind speed WS maybe. It does, and again, it doesn't matter. You just have to be able to remember it. Or average.
Oh, I just noticed that you gave us the already updated one.
Oh, I did. See, so
Yeah.
I'm screwing myself and helping you guys out. No, that's fine.
No, that it's good. We need to know how to do this also. So
yeah, exactly. It does help, because this is the annoying part, right? It's easy to push some buttons and be able to do an analysis, but this, quite literally, this can take, you know, days to be able to get your data in the format that you like. So and yeah, it's just making up names for things. Let's call this one, that's actually not a bad name, but we'll just go ETO, because that's what I comfortably call it. And shift enter. And that printed out immediately. Looks just fine to me. I don't see anything awkward. Date is in a good format. Okay. Next thing we need to do is go ahead and convert over our formats. Okay. So in my opinion, we have irregular formats in this structure because a lot of things are being read in as objects. So let's reference this frame right here, the weather.info section. And we're going to come down to number 3 here. And we see we have as type. So with the as type function, we can do the same thing, I believe, and say this column as type and then float. But let's double check. Why didn't pandas pop up? Or not pandas, there we go. Pandas as type multiple column reset. Yeah, so it's the exact same pairing structure, it's key value pair, which actually makes it easy for us. It kind of makes it easy for us because we can take these from here and copy them down. We'll still have to do some reordering of things to make sure it makes sense because obviously the pairing structure has changed here. So like ETO right now is being read as an object. We want ETO to be read as a float. Total solar is being read as a float already, so we don't need to change that. Total precipitation is being read as a float already. We don't need to change that. Wind speed, max wind speed is being read as an object. We do need to change that one over to a float. Why is ETO being read awkwardly? Must be missing a parenthesis. Oh, I'm missing a parenthesis right there. That one needs to go. Max gust speed is now, I don't remember. Max gust is now max. Nope, that's max WS. So this one actually needs to be deleted. This is the one that we need to keep. Average wind speed. Let's double check. Average wind speed is being read in as an object. We do need to keep that one. It needs to be read in as a float. And next up is relative humidity. Relative humidity is being read in as a float already. Don't need to do anything to it. Dew point is being read in as an object. We do need to adjust our dew point. So we'll keep that comma there, add that in, and then we need to go float. And I'm clearly missing right there. And we'll delete all this. Average F is being read in as an object. We want that as a float too. Date is good. We won't worry about date. I think it makes sense. And let's just double check. We don't have any errors in our line of code here. Looks good. It didn't show me anything. We'll run that. Only a column name can be used for the key in a D type. Average F is not found in the columns. What do you mean? I see it right there. Maybe it's because I didn't. Wait a minute. Let's hold on. Let's print weather. I think I forgot to save weather as a new object. I did. So that's our problem here. So weather, this right here needs to be weather is equal to weather. Rename. Okay, now that's been saved as a new object. And if we print, if we print weather, we will see we do have the correct names. So now let's try that. Could not convert string to float, star 63.6. So we've got an incorrect line of data in there with an asterisk, apparently. Is that on your version, Robert?
I think it's not actually formatted the way you had it. It's because I had it like small, so it looked formatted.
Oh, gotcha.
So I take that back.
Okay, gotcha. let's see.
I had it minimized.
So I'm not gonna worry about these, but there's clearly, yeah, there's clearly something in this data here. So it's in the 2014 data. I'm actually just gonna go through here and delete this, and then I'll re-import it and rename it. The code's already done. It won't take as long as it did the first time. But sometimes it's, it really just depends. It's up to the person. But in many cases, it's easier just to go into your CSV instead of having to type out all these, because I would have to go through in Python and find this exact row and search and then write the code to specify that based on the condition that there's an asterisk in the row, I want to remove the asterisk and keep the number, but each number is different. So you have to do a for loop to run through it all. And in this instance, I literally typed the asterisk once, ran through the data by clicking. I just controlled F and searched for an asterisk, found them all, and it looks like we've got it updated besides these NAs. And those NAs are going to get deleted because it's in a row that we don't want. So that's a pretty easy little fix there. And we're ready to save. Use that format. Should be good to go. I'm going to go in here and resubmit that, print it out. Looks exactly the same, no difference in the number of columns or anything. Rerun that. Make sure it worked. It did not resave. I did run that line. Yes. Okay. Why is that not working? The joys of data science. So we are going to start from the beginning. And luckily we can just reprint it all. Nothing crazy to be done. Oh, I see why it's doing that. Why did that must have just been a mistake on my part. I keep trying to rename the columns in the weather data set, and the rename function is actually down here. So that's why it wasn't fixing what I had asked it to fix. So that's just a silly mistake on my eyes. Let's run that. There we go. Now let's print weather. And our columns have been renamed. And now we are going to rerun this. I'll get it eventually, guys. I promise. Okay. Select our columns. There we go. Rename our columns. There we go. Print our data set. Perfect. There we go. Finally. All right. Now let's try our as type statement. Still got that error. Could not convert string to float. 63.6. Huh. Are you also getting that error, Robert?
Yeah, I'm trying to figure out why. On my side.
Line 170. Let's go to our data set. May just have to delete a row. I mean, that is step 4, right? How do we handle our missing values? So it's telling us right now that the data it really doesn't like our data for some reason. So on line, of line 170 of this code, my bad, in as type NaN safe. How about we look up 63.6? Make sure that there's not another set of weird formatting. Okay, every instance of 63.6 in this data appears to be correct. So what is being read in improperly? And it doesn't tell us what column it's in either. We could try one thing. Well, there's a bunch of things we could try actually. But first thing is to get rid of all this. And we'll do one column at a time potentially. So even that threw as an error. Star. I mean, I doubt that this is a specific issue, but I will I doubt this is an issue anyone else online has had, but I'm gonna go ahead and Google it and see. There should be a way for it to tell me. Let's see, Python find incorrect value in data set. I know that there's a way we can do this. Find invalid values in numerical columns. Okay. Okay, let's see. Describe. Nope, nope, nope. Where? It's giving us the error string to float, could not convert string to float. So it would be really nice if it told us what column it needed to be in. So, same thing. Okay. Weather.info. And it won't let us run any of our statistics, I don't think, without having the correct data type, which seems correct. I mean, we can still run through the steps, but let's see what we got here. So I did weather.describe, which basically is a way of summarizing all of your summary statistics at once. So it gives us, but notice that it's only doing it for the 3 floats. It's not doing it for all of our objects in here, which of course we don't want the average of the date, but we would like to see an average of the temperature as well as the dew point, right? Those are numerical values. Wind speed, max wind speed, those are numerical values. So we'd like to see those, and ETO is a numerical value. So we are kind of hurting right now. We need to figure this out. How about, what if we subset this way? So alter how we want to represent the data. And we said AVG underscore F, comma, AVG underscore DP, AVG underscore WS, AVG underscore, I forgot my quotations, AVG underscore, nope, it's max underscore WS, and then ETO. Okay, and then we want to do those. So I wonder if we have the notation wrong, and the documentation I looked at may have also been wrong. I wonder if it's supposed to be this way, because in this declaration, basically we're saying within the weather data set, I want to select these columns and convert them to type float. See if that runs. Could not convert string to float. 63.6. So weird. Okay. It's not even giving us a. Let's go here and make sure that we don't have an issue. Let's go check our as type documentation again. Sorry about this, guys. As type Python pandas. I wonder if I forgot part of the notation. Let's see. Maybe it's supposed to be float 64. That could be the issue. because you do see here they're saying int 64 instead of just float. So maybe that's our issue. I'm going to convert all the way back. I think that is where we're supposed to be at. Let's do 64 on the end of this. And I think to do that, we are going to be required to put it back into quotations. So this may have just been a type error on the programmer's fault, aka me. And let's hope that this fixes our problem here. Float 64. Okay, that looks like it's not throwing any errors. Still in error. Let's see. Run it one more time and make sure. Could not convert string to float. Star 63.6. And that is not in our data set anywhere. Very interesting. Let's double check one more time. 63, 63, 63, 63. Okay. Well, I am not sure anymore. Anyone else have any ideas? Let's do head equals, or yeah, we'll do it that way. Weather dot head row equals all, I think is the command. No argument row. Let's try all. Cannot do positional indexing on range index with these indexers built in all function. Okay, so you'd have to recommend it all. Well, let's specify a number. I'll do 5,000, which of course it's not going to show me. I was hoping that we could see the value and see what it is missing, but it just doesn't make sense. And I wonder if it's one of these specifically. See there, it's clearly not reading the updated data because I did save this, correct? Okay, so I just hit save. Let's double check. That could that's going to be sad if that's our problem the entire time, but I'd like to fix this. All right, so we are going with weather tandem, show the details, last edited at 11:29 a.m. That is definitely incorrect. What is the name of this? We're going to save this as, we'll rename it. This is a different data set. That's why we're not getting the updated values. I'm sorry, guys. That's a silly little mistake. I'm going to call it a tandem combined 2. Save that in a new location. We'll go up here and rename this. And then we'll get the right data set in here. Tandem combined 2. Okay. Let's print weather. Make sure nothing weird happens. Okay. Select our columns. Rename our columns. Print our columns. As type. Perfect. There we go. Okay, finally got it. Sorry about that, guys. But we're in the clear now. Let's check our null one more time. Got false across the board. Let's look at our sum. We've got, sorry, I should slow down here. I got excited because we got it correct now. But this is another function. I don't know if we've talked about this yet, but you can basically combine. It's just like if you're writing a for loop, you could write all of a for loop in one line. It's just about your familiarity with the text and the syntax. It's the same thing with these functions. So for instance, in this one line we did is null. So check if there's any null. And then once it figured out where the nulls are with the is null, we asked it to summarize the is null. And then it provides us with this list where it's showing that we have a sum of all of the null instances found in our data set, and we got it as 0. We could do the same thing as we did earlier and go with weather.info. I think it's that one at least. Yeah, there we go. So no null in our data set anymore. And we're good to go. The only thing being read as an object is a date, and we may get to that today, we may not. Now we're going to move out of our data checklist It took us a little while. We're going to get some more stuff done though today. We're going to start doing an exploratory data analysis. So exploratory data analysis is an entire process. We're not going to cover it super in detail, but we are going to use it to start to look at some of the correlations found in our data. So this is called a pair plot. And basically what it does is plots every piece of data you have against every other piece of data you have to possibly show you where some correlations or trends may be in your data. And this is showing me some pretty clear trends, right? Like up here, if we look on the top left, or let's just look at this first column here, we can see a pretty clear stack of our values, not much of a shape, some shape, but less steep, so a lower correlation, some shape, less steep, downward, pretty strong correlation, upward, pretty strong correlation, correlation. So we can see some structure in this data now that we've cleaned it up and trimmed it down, which is awesome. It means that there's going to be some value for us to draw from this. Now let's go ahead and we are going to plot it in a slightly different way. And we are going to specifically plot it as a heat map so we can get some values for the correlations. So this is just these three lines right here, plot.figure. I'm specifying the plot size. SNS.heatmap. A heat map is just a correlation map, basically. And then this is just specifying the value and that it should be annotated. So it should have my column names on it. And then plot show, of course, pops it up in our window. There we go. So these are the correlation values for our data that we're looking at right now. So in our first column here, we have average temperature in Fahrenheit. We can see a pretty strong correlation between temperature and ETO, evapotranspiration. We also see a pretty strong correlation between temperature and total solar radiation, which makes sense, right? Temperature of the Earth is determined by how much sunlight we get, so that's logical. We see a decent correlation with dew point also. Let's see, another one. Relative humidity and total precipitation appears to have some correlation, 0.33, not super strong, kind of on the weak side, but in the middle somewhere. Also, wind, for when we get to our wind question, we have a strong correlation between average wind and max wind speed. That's logical. We have a medium correlation between average and max wind speed and total solar radiation and evapotranspiration. We'll see how that plays out. In my head, I don't necessarily see the trends with that one. Just based on logic, I would expect that the wind speed or the wind patterns to be more associated with the temperature, or they're kind of associated with total solar radiation. So that actually does kind of make sense. Total precipitation, we see some correlation with relative humidity. That may add us some value. Total solar radiation and ETO, again, very strong correlation. Let's see. Yeah, that looks like it's about it, right? Once we cross the halfway point, the other points are the same. So this kind of gives us an idea, right? We've got a couple of key features here that seem like they're going to be pretty good at predicting our model or fitting our data. So let's see if we can draw some of those interesting features out. So to start, we're just going to start with our simple regression. Okay, so we're just going to do a very simple linear model. This is your y equals mx plus b. And of course, it's not always going to be in that format, but this gives us a base of where to start at. So in this case, our x is the variable that we want to try to use to explain some kind of response. Okay, so in our instance, x may be let's go back up to our question. So our first question is temperature accurately predicted by one independent variable? So in that question, what we're assuming is that our y in that instance is going to be temperature, and our x is going to be one of those variables that has a high correlation to temperature that we just looked at. Let's pop that up again. And we're going to try to see if we can accurately predict the temperature based off of one of those values. And from what I see, I think it would make sense to plot temperature against ETO, total solar radiation, average dew points, and I think that's it. I think the rest of them are too weak. excuse me, too weakly correlated to get anything out of. And so that's what this linear model is basically trying to find a way to predict that value for us. So let's change these up. So in this case, we're going to make X our total precipitation. And then we're going to make our Y our temperature. So average F. We're just going to set those as our X and Y variables. We're going to pull up from scikit the linear regression algorithm. Then we're going to fit the model using X and Y. Value error expected 2D array got 1D array instead. Reshape your data either using array.reshape -1 if your data has a single feature, or array reshape 1, -1 if it contains a single sample. So we are one dimensional. So we are going to go y.reshape of -1, 1. And let's see if that'll work. Attribute series has no attribute reshape. Okay. So what we need to do, it's given us errors. Let's go check the D type of X. X is a NumPy. Oh, we can't do D type on X. Let's convert. So we need to convert X and Y to arrays, I think. So we're going to go as type array, or would it be as type? Yeah, it'd be as type array, I believe. We're going to figure it out. That's for sure. Oh, I typed a pipe in there. We don't need the pipe. Data type array not understood. How about np.array? np.array. All right. Cannot interpret. All right. Let's go Python convert to np array. Maybe it did need to leave it as an object. Here, let's check object type. Python. Okay. Sometimes you get too far in and you don't remember. Let's see, type X. Class pandas series. Okay, so let's go Python convert pandas series to array. Pandas series to NumPy. All right, let's see if we can get an example. Just the name of it, to NumPy data type array. Okay, so we are going to try that real quick. So we're going to go x dot to, oh wait, hold on, I forgot already. To NumPy, and then d type equals float 64. Still, yes, float 64. And I spelled d type wrong. There we go. Now we can convert y also using the exact same formula. So I'll just copy it down and we'll change it just to y. Perfect. Now we should be able to run our linear regression. Okay, let's fit our model, and it's just so we do still need y dot reshape -1, 1. Oh, it's not saving them as the correct variable. So we're going to run X again, save it as new X. We're going to run Y again, save it as new Y, call in our linear regression algorithm, and then run our reshape. Okay, so expected 2D array got 1D array instead. So we have more than one sample, guarantee that. I am interested to see why it is throwing us this issue. Let's see if we can match it to the array. So it is specifically, see what numbers that it shows us. It is specifically the X array that is giving us problems. And I can see that right here in the value error. So it's showing us that we have 0.2 and 0.01 in there. And if we scroll up to where we did our conversion, it shows us 0.2, 0.01 in the exact same locations. So it's the X that is giving us a problem. So it is expecting a multi-dimensional X array to try to explain our Y. So in our instance, it appears that we are going to have to use a second, I didn't know this, or I didn't remember it off the top of my head, but apparently we have to include multiple variables in there. Let's double check this notation. So that is happening in the model fit. Let's go ahead and draw, or not draw, we're going to select this error and of course, Google it. It's the best thing to do when you don't know how to do something. All right, so when passing your input to the classifiers, pass 2D arrays of shape MN, where N is greater than or equal to 1, not 1D arrays, which have shape N, comma. The error message is pretty clear. Yeah, thanks, I agree. But what if we don't want multi-dimensional arrays in that instance? So let's make sure. Oh, that's our solution right there. We can't do the reshape. Also, now that I look at it, I was attempting to reshape the wrong object. We need to do the reshape. We may need to do the reshape outside of our notation here, but it worked just fine. So that was our issue. So this is part of the problem is as you go through this, you make silly little mistakes. I don't know how many times I've done this, but I couldn't remember that order. So all we needed to do was move the reshape from the Y to the X, and that makes sense because the Y is what we're trying to predict. The X is where we can potentially have multiple dimensions trying to predict our Y. Okay, so now we've got that model. Did I put that in the wrong line? No, I think we're good. Model fit. Yeah, I think we're good. Okay, and we're going to get rid of the reshape here also. Then we're going to run this line that says model linear regression dot fit xy. No, we do need the reshape in there too. So it'll be x dot reshape of -1, 1, reshape the array. There we go. And now we're going to ask it. So now it's completely fit the model as we have requested for the linear regression. And now we're going to calculate what's called the R squared, which is the coefficient of determination. And we need to hit our reshape again. And you, of course, if you get tired of doing this, you always could save X as a new variable with the new shape. So save X is equal to X dot reshape -1 of 1. NumPy in the array object has no attribute reshape. Oh, I spelled it wrong. 2 out of 3. I'll take it as a win. All right, there we go. And now we can print out a bunch of values because our model has actually been calculated for us. Yay. And then we'll talk about all this. So if we look over here on the right-hand side in our terminal, we can see I ran a line, coefficient of determination is equal to R squared. R squared is the coefficient of determination. And that is a measurement of how well your data explains, how well your independent variable predicts and represents the association between that independent variable and response variable. So it's between, this is a measurement from 0 to 1, and the closer to 1 it is, the better. Let's go over, I think I have a tab pulled up with this in it. Yes, right there. So coefficient of determination, it provides a measure of how well the observed outcomes are replicated by the model based on the proportion of total variation of outcomes explained by the model. and it's literally just the division. So it's the sum of squares of the residuals based on the model fit divided by the total sums of squares subtracted from 1. So the closer it is to 1, the better the fit. The further away from 1, the worse the fit. So in our instance, this is a horrible model. 0.09 is absolute, or 0.019 is absolutely atrocious. Then we just have some other model characteristics. So the model intercept, where it intercepts the y-axis, is at 51. And then we also have the slope, which is negative 29. So we're intercepting at 51 and then going straight down by negative 29. So this is a horrible model. It does not fit the data well. And that is why we did it, is because I wanted to be able to show you guys that one, this works, and two, these are not good predictors. Okay, so let's go back up to our plot right here, our heat map, and figure out why. And actually, let's split this to split screen. So we mapped the average temperature, that's what we wanted to predict, as a response of total precipitation. And if we look at our heat map, here's average temperature in our first column. Total precipitation, negative 0.14 is the correlation between those. So clearly from our pre-exploratory analysis, or our exploratory analysis of our data, we could have determined that that would have been a bad fit. But that is the purpose of this exercise, so you can see when data is very poorly fit. Now what we're going to do is look at a situation where the data is fit almost, maybe not perfectly, but probably much better, significantly better, I would say. And that's what we're going to look at here. So this time we are going to map average F. Let's switch these. So what did we name? I need to look up our names of our columns because I forget. So we want our Y variable in this instance to be our average F, or average temperature. And then for our X, the thing that we want to explain our Y, in this case, we want to look at the total solar radiation, so tot solar. All right, let's run those. Get rid of that. I'm actually just going to highlight all this. This is the exact same code that we just wrote. I just changed the X and the Y. So we can very quickly run through these points. There we go, calculated everything. So using solar radiation as our model fitting variable, so the thing that we're trying to associate or determine the association to our temperature, we can get a coefficient of determination, a relationship between these two variables of 0.649, okay, versus the 0.019 we had when we were doing precipitation. Okay, on top of that, the model now is intercepting at 28.8, which would be the total solar radiation value on the y-axis. And then, or no, excuse me, that would be the temperature value on the y-axis, because that's our response variable. And then our slope is equal to 1.44. Okay, so totally different model. And if we go back up to our heat map again, let's see if that makes sense, right? So for total solar radiation, we had a observed correlation in the original data set of 0.81 when we're comparing total solar radiation and average temperature. And when we actually fit total solar radiation to be the explanatory variable for temperature, we see that we get almost a 65% fit, or 65% association or relationship between those variables. So a much better fit than we had in our first model, and that is really good news. So, okay, so that's those two. Now, as you saw from me messing around and messing up this lab, one of the things you can do is come in here and specify multiple variables. So with total solar radiation, for instance, we could come in here and also say ETO, because ETO potentially is a good fit for predicting temperature. So real quick, in our last few minutes, let's try to do that. We're gonna now we can get rid of this reshape factor, because we will have a two-dimensional array as the software is expecting. So let's really quick run these two lines, make sure they read in fine. Oh, key error. What are you expecting there? Error. I think possibly the issue is that I need a bracket here. I need to close that one off there. And then I need to specify again whether. And this is why it's important to read your documentation, is because these little things take up a lot of time. There we go. All right, now let's read in our Y. So what we've written here is that we want X to represent an array of total solar and ETO of evapotranspiration. Now we're going to convert them to NumPy arrays and run all our code again. We got an error. We're missing a line in model fit right there. The regression ran fine. So from here through 169, got another error. It still doesn't like that model fit. Found input variables with inconsistent numbers of samples, 2 and 5358. So it's telling us that ETO. You know what? I'm going to leave this alone for now, and we're out of time anyways. So I will, if you guys need to leave to go to another class, you can. And that's totally fine. That's totally acceptable. If you want to stick around, I'm going to continue to record the machine learning for multiple regression section. And so I'll give you guys a couple minutes to figure that out. So if you want to stick around, you can. Otherwise, you're free. Just a reminder, the homework is due on Friday now, I believe, but Friday by midnight. I'm saying it here, so that's the date. So Friday by midnight, please have your next homework due. There is the link on MyHeritage. You also can email it to me or send it to me on Discord, whatever works. And besides that, thanks for being here. You are free to go, and I will see you next week. Robert, are you sticking around?
Yeah, I have 5 minutes before I can go.
Okay. All right. So obviously we didn't make it through all the material today, so I'm going to keep talking and we're going to get through this machine learning section, which will be available online. But the point of our multiple regressions and linear modeling here, or not multiple regressions, simple regressions, is the fact that weather data is complex. The Earth is not an isolated region. Each state does not stand alone. The Earth is a biosphere. So everything has an effect on everything. And it's acting as a singular system that has an overall weather trend. And that weather trend is what we refer to as climate. Okay, so in order to accurately model weather, we have to include many different variables and iterations of our variables in a model to be able to accurately predict how the model is going to respond. So what we're going to do now is start working on scikit-learn and machine learning as a way to basically add more variables and provide more explanation for our data set here. So the first thing we need to do is import another library, and this is just scikit-learn for model selection, and we're importing the train test split, which is just a specific algorithm. So we'll go ahead and pop that in there. Next thing we're going to do is use a NumPy array random seeding, and we're going to save that as 0. This basically saves the exact environment we have. The next thing we're going to do are define our training data set and our test data set. So when we're doing machine learning modeling, you basically have to split your data into a training set and a test set. It depends on how you want to split it in many instances. In our case, we're going to do a 70-30 split. So we specify, if we look at this line of code right here, we tell it that there are now going to be 2 new objects that come from this data set. Those will be DF for data frame train and data frame test. Okay. And those will be equal to the train test split algorithm. And that train test split algorithm has a bunch of different parameters. In our instance, we're going to specify the data set, which is weather. We're going to specify the train size, what percentage of the data is supposed to go towards training. We're going to do 70%. The test size is going to be 30%. And then the random state is equal to 100. So that is just dividing things up so that we can use them later on. And let's check the shape of our training data set and the shape of our test data set. Our training data set has a shape of 3750 with 9 columns. Our test data set has 1608 rows with 9 columns. Okay, so we kept the same number of factors or variables or parameters and just split it 70-30 based on the number of observations. Now what we have to do is scale the data. So if we handed this directly to a machine learning model, there's not a guarantee that it would understand it because there's so much variability in it. So we have to take all the data and essentially normalize it and scale it and condense it down into a measurement or value that is indicative of the value and scale of the entire data set. So let's say that right now we have a 1-to-4 ratio. This is going to take this algorithm is going to take that and take it from 1-to-4 ratio down to a 1-to-1 ratio that the computer can understand. So I hope that that makes sense, but you have to provide some kind of scaling for you to then be able to predict and train your model. So again, we're going to import another algorithm. This is called the min-max scaler, and it does exactly that. It scales. So we're going to create the scaler that is the min-max scaler. And then we are going to specify the variables that we're interested in our training data set. So in our instance, let's check our documentation here where this project was originally done. I believe we want to list all of our variables there. Yeah. So we want to list all of our possible explanatory variables in the numVars object. So in our instance, again, I don't remember. So we're just go weather.info and call up all of our possible explanatory variables. In our instance, we have quite a few, but average temperature, average dew point, average relative humidity, average wind speed, max gust speed or wind speed, total precipitation. I just realized the thing that we want to predict is the average temperature. So we actually don't want to put that in our variables right now. Let me double check again. I think we don't want to put it in our variables, but we may need to be able to predict the correlation between. Yeah, we're not training a model yet. We're checking the model. So we can leave average temperature in there. And again, don't be afraid to check your documentation or your sites when you get to this point. Even if you've done this 1,000 times, you are always going to forget something. So just trust yourself. So we're listing all of our potential variables in this new object. And now we are going to scale all of those variables down so that they match our training data set. We're going to do a quality check on our data. Looks like none of the counts got altered. Seems okay. I don't see anything crazy out of place. The big thing here is that we just don't have any missing values. Like that's the hard stop. If you have missing values at that point, we've got an issue. Then we're going to check the correlation again for this new model that we've scaled, and we're just going to see if it makes sense. And it looks like the correlation factors are almost identical to what we had in our initial data set. You'll see, like, for instance, total precipitation in the first column here originally was negative 0.14. It's now 0.13. I believe correlation between total solar and average temperature was 0.84. It's now 0.8. ETO is down to 0.89 instead of, I think, 0.91. So really not much of a difference, just a slight difference that allows the computer to understand and normalize and scale down to match the current situation. Okay, so now what we're going to do is divide our X from our Y. So divide our independent variable or explanatory variable away from our response variable. And so to do that, we basically just have to tell it what it is removing from that df underscore training object. And in our instance, we want to try, in this case, we want to try to predict our average temperature value. So we're just going to pop off, which is a removal technique, the average F from our Y training data set and create that. And then X is going to consist of all of the remaining variables. Okay, now that's done. And we are actually ready to start building models. Okay, so this is a iterative process in this structure. It does not have to be an iterative process, but this shows you the complexity of building these kind of models in an instance where you might have to do this. So the first thing that we're going to do is import the stats models API, which is just a module. And once that is imported, we are going to add a constant to our data set. And to do that, it is simply x underscore train underscore lm linear model equals sm for the stats model dot add constant and then x train. And then we tell it what our constant is going to be. So in our instance, we just want to pick something. For this data set, we're going to use relative humidity, which relative average relative humidity. So it'll be AVG underscore RH, and we will run that. And then we are going to create our first fitted model. So we're going to say linear regression equals sm.ols, and OLS is a specific regression model. So let's look that up real quick. So OLS is ordinary least squares, and it's a common technique for estimating the coefficients of a linear regression that we're working on. So that's exactly what we're doing. So this is our way of fitting the model for that entire feature set that we provided it earlier. So we tell it LR for linear regression is equal to the statistics models dot OLS, the ordinary least squared, and then we tell it what we want it to do. So we want it to take the Y training set and match that up to the X training set for the linear model with the constant added that we did in the first part, or the first step, and then we're going to fit the data. So we'll run that, runs just fine. Now we're going to look at the parameters. So we can see our constant is showing as a value of 0.79. So that's essentially like an intercept. And then we see that average relative humidity has a negative correlation with our Y training value, which is the average temperature value. And we're going to summarize this and see how well this fits our model. So this is our summary of the results for that regression model that we just ran. There's a couple of things that we need to run through here to make sense of. Okay, and I think I've got them written out down here, right here. So when we're checking the fit of a model, we want to look at two factors that are called the AIC and BIC. AIC versus BIC. And this is something that you can Google. AIC and BIC are basically constants and measurements. It's they're named after people, but I can't remember who right now. Let's see. AIC statistics. The AIC is the Akake Information Criterion. So it's used to compare different models and determine which one best fits the data. And it's calculated by the number of independent variables used to build the model and the maximum likelihood estimate of the model. Okay, so really in this class, you don't have to be able to exactly explain the AIC to me. What we're looking for though is that the AIC not be too large, not be too small, and we're going to compare this AIC and BIC between the models. And kind of the standard with the AIC and the BIC is if a AIC or BIC between one model or another model is more than two numbers away. So if it's a count of two away, either greater than or less than the previous model or the current model, then the one that is lower, the AIC or BIC that is lower, is the better fit. Okay. Now, anything else interesting that we see in here right now? Well, we can see our R squared value, which is that coefficient of determination based on the current model with only one parameter, the average relative humidity as our constant. We can see in our X training data set, excuse me, we can see we have an R squared of 0.501. That's not super great. It's exactly right down the middle, 0.5, right? It's kind of correlated essentially is what that means. And then we also see that our p values, which are a measurement of how significant something is, we have 0 for both our constant and our average relative humidity. So we're not getting a ton of information at this point in time. And as of now, this model, according to the AIC and BIC, is likely pretty underfit. This is not a good representation of the data. As I was saying, the Earth is a very, very, very complex system, and it's going to take a lot of factors for us to be able to accurately represent this data. So where do we go next from here? Well, where we go next is that we keep building on this model. So we're going to assign another variable to this model, train it with that extra variable, and then we're just going to keep going, and we're going to keep adding as we can until we get a well-fit model. So again, we're going to do the same thing. We're going to come in here on line 237 where it says x train lm equals x train, which is our data set. And then we were using average relative humidity. And the next variable we'll add in is our wind speed. And let's scroll up a little bit. Our wind speed, we'll do average wind speed, not max wind speed yet. So it'll be AVG underscore wind speed. We'll train that, or we'll split that, excuse me. We'll call on our stats models API. We'll run the add constant again. We'll fit our linear regression, and we'll look at our parameters. Okay, still a negative correlation, and then we'll print our summary. All right, so by adding in that second variable, we now have a slightly better fit model, just barely. Okay, so we see that we have an AIC and BIC of negative 5,178. So technically, this model is worst fit in comparison to the last model. Remember, an AIC or a BIC, you want it to be lower. So if we compare it to our last AIC and BIC, we had a negative 5023. And in this instance, we have a negative 5178. So it is a worse fit, but we do have a higher R correlation value. In general, though, this is not a well-fit model. So we're going to have to keep iterating over this again and hope that we can find some more variables that will add some explanation in. So let's pick one that likely will add in some complexity and provide us with some value. So we're going to go in here and immediately we can just start building our next model. So we'll copy in, we're going to do average relative humidity, average wind speed, and then we're going to add a third variable. This time, let's pick one that should add a lot of meaning. We're going to add in total solar, tot solar, because we saw that had a high correlation. We'll train that. We're going to go in here and rerun all the same lines of code again, retrain our variables, look at our correlation values. Now you can see total solar is actually positively correlated to temperature, average temperature, which we did based on our initial analysis. Let's look at our summary. And we can see that our R squared value has gone up quite significantly. We're now at 0.657. We also, it appears that our AIC is still getting worse, though. The model is not a good fit at this point in time. So we've got to keep adding things. Or in this instance, it may be worth it to actually subtract things, right? So we're seeing that average relative humidity and average wind speed are not providing us with value. So why not just get rid of them and retrain based on the total solar radiation? Maybe that'll provide us with a better fit model. So we're essentially we're reconstructing our model from a different angle. There we go. So let's see what we've got now. All right, so we've got a higher R squared value. It appears our model is slightly better fit now, negative 6284 versus negative 6426. So total solar radiation did provide us with a better fit of the model. It is still not completely explaining the model though. So we will have to keep adding in more variables. So let's scroll up, find our other variables. We're going to copy our code here and build model 4. So we've readjusted our plan basically. We deleted average relative humidity and average wind speed from our model. They were not providing us with any relevant information. Now we are rebuilding the model using total solar as our primary variable at this point in time. And now that I think about it, we actually have to go back a couple instances here. We need to add a constant. Well, we used relative humidity. Let's retrain from up here. And I think that will make more sense because we need to pick a new constant. You know what? I backtrack on that. I've been misrepresenting this. If we just Google real quick negative AIC statistics, what if an AIC is negative? There's nothing special about a negative AIC. The smaller, the better. Still, so if it's more negative, it's a better fit. So as these numbers were getting smaller, the model was actually getting better, and specifically when we added in the ETO, the model got significantly better. It went down by 2,000. So this ETO is providing us a lot of value here. What that also means is that we can go in here and re-add in our, we can alter this back to its original state. So we can add in relative humidity and wind speed again. While they aren't apparently or like obviously providing any value, they are still probably telling the model something, and they were helping us lower our AIC and BIC. So they were technically fitting as we expected. Now let's go in here and add them into model 4. And in this one, we also have ETO added. We got an error. Put the comma in the wrong place. And let's get through these. All right, there we go. So there's our coefficients or our correlation values here. So again, we're still seeing that negative correlation, and we have a 95% correlation with ETO, with the evapotranspiration, and our average temperature. So evapotranspiration is very, very heavily influencing this model, and it's a great predictor of the model. Now we're down to a negative 9,000, still getting better. We have an R squared, or a coefficient of determination, 0.83. So over 8% of the relationship can be explained by the current model. That's not bad. Most people at this point would probably probably stop, like that for machine learning, for the current state of machine learning as a science. I think that a model with 0.83 fit would probably be accepted for scientific publication. But we're going to keep going. We're going to see if we can get over 90% or 90%. You look down here at our actual coefficients and our p-values. We're still looking pretty good. The one thing I see now that average relative humidity has jumped up to 0.036. I left a note for you guys right here or right here. So we've got to check for, we've got to check our p-values. Remember, we want to keep p less than 0.05 because that means there's less than a 5% chance that the result or outcome that we're seeing is by chance. If it goes over 0.05, then we start to get a little concerned about the reliability or the probability of that outcome. So if that happens, all we'll have to do is take the average relative humidity out of the model. All right, so that was model 4. Let's keep adding on to it. Let's see, what else do we have that we can add? So we can continue to add, we've got to do total precipitation, and we've also got to do dew point. So we've got 2 more models to fit, and I think we are caught up. Oh, we also got max wind speed. So 3 more models. And the points, the reason why we're iterating one variable at a time is there is technically the chance, I think technically, that as we're training the model, if we put multiple new variables in one instance, it may not get as much of the finite detail out of the training process as we'd hope for. So that's the reason for doing them all separately. Now that could just be total nonsense, but I think in the process and the procedure that we're using, that is the correct methodology. So again, let's get back to training. So on model, this is actually model 5. I added in average dew point. We're just running through our same lines of code here. Let's look at our parameters for our coefficients. We see that ETO, as we added in average dew point, ETO dropped down from 0.95 in this last model down to 0.20. So that'll be interesting to see how that's affected the model fit. But average dew point now is at 0.74 for the new variable. So let's look at our summary. All right. Now we're fitting over 99% of our data. So for our R squared, for our coefficient of determination, which is the percentage or the amount of the relationship between our explanatory variables that are predicting our response variable, we have 99.6% relationship or association between the explanatory variables and the response variable at this point in time. The AIC and the BIC are down to negative 2.314, which would be 23,140. So we went from a negative 9,000 to 23,000. So we more than doubled the model fit according to the AIC. Remember, the more negative, the better. So this model is a much better fit than we had previously. And honestly, at that point, once you hit 99%, right? So we jumped up from 0.83 in the last model to 0.996 in this current model. We're pretty well set. There's not necessarily a reason to continue to add when you get that high. There are still more variables that we could place in the model, but at this point in time, it is unnecessary. So the next thing we're going to do is check what's called the VIF of the model, the variance inflation factor. So the other predictors in the model, the inflating model fit. It's a test for linearity and multilinearity, and it determines the strength of the correlation between the independent variables. So we just want to make sure that we're not overfitting and missed where model is perfect, right? And that is a fair concern for this model, right? When we now we have a coefficient of determination of 0.99. Okay, so it is possible that we have over this model at this point, and we may need to make some adjustments for that. So what we're going to do to calculate that is calculate the VIF, the variance inflation factor. I think that's what it's called. Hold on. Variance inflation factor, yes. So we are going to create a new object called VIF, which is a pandas data frame. Let's go ahead and run that. And we're going to say that VIF the features of VIF are going to consist of the X train columns. So we're basically going to add all of the X columns into the VIF under a column called features. And then the VIF features are going to, or the VIF is going to be calculated for us by taking a algorithm or function called the variance inflation factor and providing with the X train values. And then we're going to run a for loop and say, for I in range of the X train shape, and it'll calculate all of the variance inflation values for every value. Okay, so I took a step away for a second. I got an error that said could not convert string to float for date. And to be honest with you, I completely forgot that the date variable was in the data set at this point. Having the date in here is obviously going to, or possibly going to skew our model. It would be, there's a potential that the date causing the correlation between the observation and accounting for that variance by providing that temporal characteristic. So what I'm going to do really quick is create a new data set that does not include the weather data, or not, excuse me, not the weather data, does not include the date. And we're going to rerun through this training process and make sure that it did not manipulate our results in any way. So, and the nice thing is we've already written out all the code, so we can just Control Shift Enter, make sure everything looks okay, rerun, and it got the exact same result the second time around. So the date was not affecting the actual fit of the OLS regression or of our model overall. It was just affecting the VIF, which is that variance inflation factor. So with the removed, now we should be able to calculate the VIF. And we are going to go ahead and call on that package again for the VIF, and we're going to run through these 3 lines of code. All right, so we're going to go ahead and keep running through the VIF, the variance inflation factor. The first thing we're going to do is we are going to call in this model, the variance inflation factor algorithm from the stats models package. Then we're going to create a new pandas data frame called VIF. Then we're going to assign a column in the VIF data frame to the X train columns. So we're going to take all those columns, put them in one thing called features. Then we're going to have the computer automatically calculate the variance inflation factors for us and store those in a new column called VIF in VIF. Then we're going to round the VIF. That line's already there. That's just a round function that's built into Python. And then you tell it what column you want, and you tell it how many digits you want it rounded to. And we're going to ask it to sort our values in descending order. And then lastly, we're going to print out the VIF. And we generally want the VIF to be less than 5. And so you can tell from our model over here on the right, we are super duper overfit. Okay, and that makes sense based on this R squared value. We have a R squared of 0.996. There's no way by only using 1, 2, 3, 4, 5, 6, 7 features, we would be able to fit a 99, or that we should be able to fit 99% of the weather data to a model. That's almost a perfect fit. It's very unlikely. Our p-values are good, but this VIF is telling us that we've overinflated our data drastically in comparison to what it should be. So if we were going to keep going, we'd have to keep iterating over this model. And we basically have to start by cutting some of these features out. So everything on the right, everything except for the total precipitation needs to be removed, which is it's not horrible, but this is why you should check the VIF after each model instance, right? So if I was doing this correctly, I would have taken this VIF code and dispersed it throughout our models. So like right here after on line 233, after we look at the model summary, I would then look at my VIF to check the fit of the model. So let's go ahead and do that. And so obviously, if you've overfit your model, you've got to rebuild your model. You've kind of got to start from square one. And this was just an example. This was an example to show you the good, the bad, the ugly of this process. And this is the direction we'll be heading. So to summarize everything up, today we covered the basics of statistics in Python. We practiced some linear regressions. We practiced a couple multiple regressions. And then we also started learning machine learning. And machine learning is a whole slew of algorithms and architectures and packages that we'll need to know. But in our instance, we use a very simple package called scikit-learn to fit a basic multivariate regression model called OLS, or ordinary least squares regression, and tried to determine a model that was a good fit for our weather data. What we found by fit our data is that we can properly, but what we found out in this case is that we overfit the data, which happens plenty of times. And when you overfit the data, unfortunately, you just have to restart. So those are the things that you have to pay attention to. Next week, we're going to go into machine learning more in depth, and we'll start to then add on the AI aspect, which is the predictive aspect. So once we fit our model good or well, we have a well fit model. It's not overfit, it's not underfit. Then to use it. So thank you guys for being here. I hope you have an awesome day, and I'll see you next time.